Hi students. Okay, so last video you learned about how to create or how to generate the non-systematic cyclic code. Okay, that is the encoder of a non-systematic cyclic code. Here you are going to learn about how to generate the systematic cyclic code. Okay, so here we need to understand that for a systematic cyclic code mainly we use a division circuit. That is one thing you need to understand. In the non-systematic, when you are going to generate the non-systematic cyclic code, you are using a multiplication circuit. Here, for a systematic cyclic code, you use a division circuit. So, before going to the division circuit, I want to tell you all why we are using this division circuit. Okay, for that, to understand that, you need to understand the term of systematic cyclic code. I know that all of you already know the meaning of this, but still I want to show you in terms of its polynomials, because by expressing in terms of polynomials only I can justify myself to you why are we using this division circuit. Okay, so we all know what the systematic cyclic code is, in which you know that in the systematic cyclic code is in which the code word, any code word that you're going to take, that code word will consist of part parity bits and part message bits, right? It will contain, so for example, if this is your message okay, if this is your input message, that is u0, u1, u2, u3 up to uk minus 1. Why? Because this message is of k bit. So from u0 to uk minus 1, this is your message. So now you're going to encode this into a systematic cyclic code. So for that, your output code word should contain, partly it should contain the parity bits and partly it should contain the actual message itself. So how does your code word looks like? Your code will be looking like, so first I will represent the parity message, the parity bits like this, that is P0, comma, P1, comma, P2, okay, and so on. I don't have to write the remaining, and it will become, here it will become Pn minus k, okay, comma. Now this is the part parity bits and part message, and this is your message. u0, comma, u1, comma, u2, comma, up to uk minus 1. See, this is how we represent the systematic cyclic code word. One code word of a systematic cyclic codes will be looking like this. That is, here you can see there are totally n minus k bits. Here there are totally k bits. So n minus k plus k is equal to n, which is the number of bits of the output code word. Always the output code word will have n bits. So n minus k plus k, right? So here the P represents the matrix in this set of parity bits, which is represented as P0, P1, P2 up to Pn minus k. Okay, so now if I'm going to represent all these sets in terms of its polynomials, how does it look like? If you want to represent all this in terms of polynomials, then I will say that first I will start with u of x, okay, the input message. So the input polynomial will be looking like this, right? That is u0 into x raised to 0 plus u1 into x raised to 1 plus u2 into x raised to 2 plus, and it goes on up to, and the last one will be uk minus 1 x raised to k minus 1, right? That we discussed this in the introduction of the cyclic codes. That is, a k bit message will have a degree of, its polynomial will have a degree of k minus 1. In the same way, when I'm going to write, let me write the parity bits. So here it will become p of x, capital letter p of x, okay? Capital letter p of x is equal to, and it's represented as p0 plus p1x plus p2x square plus, and it goes on and up to, totally there will be n minus k bits. So n minus k x raised to n minus k minus 1. This minus 1 is coming because it starts with 0, that's why. Okay, so therefore this is of k bits, this is of n minus k. So this degree is k minus 1 and its degree, this degree of this is n minus k minus 1. Okay, so what about your actual code word, your code polynomial, that is capital letter V of x? How is the code word of this looks like? It looks like this, right? It is p0 plus p1x plus p2x square plus, and it goes on up to, the last word will be Pn minus k x raised to n minus k minus 1 plus, next letter is u0, so it will become u0 into x raised to n minus k, because after the next polynomial after this is the next polynomial, the next degree after this, the next power after this will be plus 1, so therefore that minus 1 will get cancelled, and after this the next value will become u1 into x raised to n minus k. So after n minus k, the next value will be n minus k plus 1, plus it goes on u2 x raised to n minus k plus 2, and this thing goes on up to the last term would be u k minus 1 x raised to n minus 1. This is how the code word polynomial looks like. See, so this is how we represent the terms. So now if you look at this v of x, okay, if you look at this v of x, you know, you can see that from here to here, let me use another pen, yeah, from this point, from this to this point, this is nothing but your p of x itself. From here to this term, this is nothing but p of x itself. But from here to here, you need to take, what do I need to take? I need to take x raised to n minus k common. Okay, so what do you think will happen then? So this is p of x. This is nothing but from p0 to p n minus k coefficient. From p0 term to p n minus k term, this whole thing is nothing but your p of x. So I can say that v of x is equal to p of x plus, and what about this, after this term, that is from u0 to uk minus 1, if you take x raised to n minus k common, if you take x raised to n minus k common, you will get x raised to n minus k into u of x. The remaining term will be this actual term itself, which means this is nothing but x raised to n minus k u of x. This is the another way of representing the code polynomial. That is, this is nothing but your parity polynomial plus your x raised to n minus k multiplied with your input polynomial. So this is how we express the term. Okay. So now what I'm going to do is, what you need to see here, what you're trying to do is you're trying to actually create the systematic cyclic code word. You're trying to create this stuff, this letter over here. You're trying to create this, or you're trying to create this. Okay, so this is what you're trying to, that's what's the meaning of the word encode. You're trying to convert this into this, and or this into this. Okay, but one good thing is that this is partly your input message and partly your parity bits, right? Like I told you that. So here we already know what the input message is. That is already available to us. Okay, fortunately that is already available to us. We all know this. All of us, when we are going to transmit the input message, we already know what is this, or we already know what is the input polynomial. We know both of these values. So what we actually don't know, because here the same thing is what we are going to transmit over here. So what we actually don't know is this parity bits, or this parity polynomial is what you are trying to create. So what you need to do is you need to create a circuit. You need to create a circuit in which you can actually generate the parity bits. Okay, because the input message you can transmit it on the spot. All you have to do is simply pass that input message into the output. That's all you need to do in order to get this values from here to here. But from here to here, you need to create a circuit in which it will generate the parity bits. So that is what we are going to do over here. What thing is how to find. So this is what you're going to do. We are going to draw a circuit in which how to find this value right here. How to find p of x, and that circuit is called as the division circuit. Okay, so the reason why we're using division circuit is because one thing you need to understand, in this systematic cyclic code, we don't use this equation. V of x is equal to u of x into g of x. This is the equation you have studied earlier, but you need to understand that there is a difference between this equation and this equation. This equation is used to create non-systematic cyclic code, whereas this equation is used for creating the systematic cyclic code. For non-systematic that you have studied in the last class, we are creating this circuit, and this circuit can be created using the multiplication circuit. But here, to do this, we can't use this circuit, because if you use this, you are actually going to create a non-systematic cyclic code. So that is not what you want. You want a systematic. But one thing is that whether it is a systematic cyclic code or a non-systematic cyclic code, this v of x is always having a common property, and that is that it is a factor of g of x. Yes, we have learned that in the previous class. That is always the output code word of a cyclic code word. The cyclic code word is always a factor of g of x, or the code word, the output code word is always a factor of g of x. See, for non-systematic, that factor is u of x, but for a systematic, that factor is not u of x, it is something else. So what I'm going to do is that I'm going to name that factor as q of x. So in other words, v of x is equal to q of x into g of x, okay, is equal to p of x plus x raised to n minus k u of x, okay. So this is how I'm going to write, okay. Now, so this is how we are going to represent this, okay. And then what I'm going to do is that you need to understand that every plus that I have written is not your average addition. Again, I am repeating this plus actually represents the XOR function. There is no minus or subtraction or anything like that in this portion, in the subject, because every value that you see here, every coefficient that you see here are nothing but pure binary values, and only pure 1-bit binary operations are what you would apply over here, okay. So which means that what I'm going to do is that I'm going to put this p of x over this side. I'm going to put this p of x, I'm going to bring it over this side, so I will get x raised to n minus k u of x is equal to, and this will become q of x into g of x plus p of x. This is how it looks like, okay. So like I said, what we are trying to do is you want to make a circuit that will create this, because we already know what is u of x. We already know what the input is. We are the ones who are transmitting it, so we know what the input is, but we don't know what the parity bits are. So here the main problem is that we need to find the parity bits, and after finding the parity bits, we can then first we'll send the input bits, and then we'll send the parity bits. Okay, we always send the input. We always send the higher degree coefficients first. Okay, we'll send this value, then we'll send the next value, then we'll send the next lower value, and it goes. So that's how we always send it. Even for your mathematical operation also, we'll first express it by writing the higher order coefficients first, okay. So here in this circuit over here, if you look at the circuit, right, in school you have actually studied this equation. That is, we say that dividend is equal to divisor into quotient plus remainder. We have always studied this equation over here. So here this is nothing but this is called as the dividend. Dividend is equal to divisor into quotient plus remainder. The quotient is this q of x, and the divisor is this divisor g of x. G of x is the divisor, q of x is the quotient. That's why I give the name as q of x, to represent that this is actually the quotient plus remainder. So now you know, here you are trying to find the value of p of x. So now you know how to find the value of p of x. P of x is nothing but the remainder of this division operation. That is why we are using a division circuit, because p of x, the one thing that you are trying to find, this p of x, that is actually nothing but the remainder of the division operation, and that is what you need to find. You don't need to find the quotient is not relevant over here. It's not the quotient that you want. You want the remainder. So for that purposes only, we are actually drawing the division circuit. So now why we are so how this the working of the division circuit is that when you are going to divide the circuit, right? So here this circuit is actually based on the value of your divisor, right? So let me write this equation. So here this is the divisor. So divisor means let me put g of x over here. So this will become x raised to n minus k u of x by g of x is equal to quotient plus remainder by divisor, right? So here what you're trying to do is you need to create a circuit of this type. You need to create a circuit of this type because we already have u of x. So from u of x you can create a circuit that's looking like this, and then from this value, when you're going to create a circuit like this, your input will be u of x as usual. Your input will be u of x, and then your output, the first output that you will get will be your quotient itself. You will get the quotient coefficients first. First you will get the quotient, okay, and you know, like I said, you don't need the quotient, so you have to wait for that time period. So first you will get the output as a quotient, and after getting the quotient, from that same output you will get the remainder. So that's how we create, or that's how we find the values of p of x. That is, first we divide the circuit, we apply the u of x, or we apply u into the circuit, into the division circuit, and then the division process will start. And then what happens is that the quotient will be first created, and after when the quotient is created, the remainder will come after that. Okay, so this is the working of the division circuit. So we will explain that now. So now we will move on to the division circuit. Okay, I will show you how we going to create the division circuit. So for that, let me use an example. Okay, so in this example, what I'm going to do is I'm going to assume a 7-4 cyclic code. Okay, 7-4 cyclic code means n is equal to 7 and k is equal to 4. So in that, I'm going to assume that u, okay, my u is nothing but 1 0 1 1. Okay, which means when you're going to transmit the circuit, when you're going to insert the value, first this one will enter the circuit, then this one will enter the circuit, then this 0 will enter the circuit, then this one will enter the circuit. Or in other words, u of x, okay, u of x is equal to, let me, how it is written, it will be 1 into x raised to 0 plus here it is 0 into x raised to 1 plus 1 into x square plus 1 into x cube. So 1 plus x square plus x cube, this is the corresponding polynomial of this code. And I'm also going to assume that my g of x, okay, my g of x is equal to 1 plus x cube. This is the same g of x which we have used earlier in the previous videos. Okay, so these are the two things you need to know if you're going to draw the encoder of a systematic cyclic code. Okay, this you need to know the value of this or this, and you need to know the generated polynomial. So now the next step, what I'm going to do is that I'm going to multiply u of x with x raised to n minus k. So which means that here n is equal to 7 and k is equal to 4, which means I need to multiply x cube with u of x. So if I multiply x cube with u of x, what will I get? I will get x cube plus x raised to 5 plus x raised to 6. Okay, so and then what I'm going to do is I'm going to divide x raised to minus k u of x with g of x. I'm going to make this a division operation, so that from here I will get the remainder p of x. This is what I'm going to do. Okay, so for that, first let me show you how the actual division operation is being done, and that I think almost everyone know how it is done, right? So first, in order to do that, this is my dividend. Okay, this is my dividend and this is my divisor. Or in other words, if I'm going to draw the division circuit, first I will write the higher order coefficients. First, x cube plus x plus 1 divide by, and here it will be x raised to 6 plus x raised to 5 plus x cube. Okay, so how the division operation, we all know, right? We always look for the first term to get cancelled. That's what we always do. So let me cancel the first term. So you will get over here is x cube plus, here it will be x raised to 4 plus x cube. Okay, this is x raised to 6, sorry. Okay, this will be x raised to 6, x raised to 6 plus x into x cube is x raised to 4, x cube into 1 is x cube, and then we simply apply the XOR operation, because plus and minus are all nothing but XOR operation itself, which means these two will get cancelled, these two will be combined, and you will get x raised to 5 plus x raised to 4, and these two will get cancelled, so you will get x raised to 5 plus x raised to 4. So now I want to remove x raised to 5, so what I'm going to do is I'm going to multiply it with x square, and if I multiply the x square with this number, I will get x raised to 5, so that's how I will cancel each other. So I will get x raised to 5 plus x cube plus x square. And then I will apply my XOR operation. These two will get cancelled and you will get x raised to 4 plus x cube plus x square. Then what I'm going to do is I need to cancel this x raised to 4, so I will multiply this divisor with x, right? I need to multiply it with x, so I will get x raised to 4 plus x square plus x. So what will happen is that these two will get cancelled and also these two will get cancelled, so it will be nothing but x cube plus x. So you see, that's how this operation is actually much more easier than your ordinary mathematics operation. There you have to find the subtraction. Here there's no subtraction. Whatever operation you do, whether subtraction or addition, everything is nothing but XOR itself. That's why this is so easy. And here now I'm going to cancel x cube. So to cancel x cube, I will just need to multiply the divisor with 1 and I will get x cube plus x plus 1. And these two will cancel each other, and you will get the remainder as 1. So here the p of x, the remainder over here is p of x, your parity bit. This is your remainder and this is your quotient q of x. So this is how the operation is being done, right? So the same operation is what we are using over here. So if you look over here, what is actually happening is that you are actually multiplying this with your quotient, and then after that you will be doing for every step with the shifting operation you apply the XOR operation, right? You apply the XOR operation. So that is what this division operation is all about. It's a combination of XOR operation and shifting operation, XOR and shifting. So that is how we need to remember. This is how you need to remember to draw the division circuit. So to draw the division circuit, what you need is nothing but a series of shift registers in which at every input of the shift register, wherever there is a connection, there will be an XOR operation. That's all. So to draw the division circuit of this, okay, all I need to do is first I will draw the shift registers, and at every input of the shift registers I will draw the XOR operation. So this is how the general block diagram of a division circuit looks like. That is, there will be a shift register like this, XOR operation with a shift register. There will again be a XOR operation with a shift register, and it goes on. And last also there will be an XOR operation with the shift register, okay, and then this operation over here, this you apply this is represented by a switch, where every switch represents the coefficient itself, okay. This is all will be fed back. This is how you represent the division circuit. SR1, SR2 up to it looks like how many divisor is there. So here there are so how I represent this, I will call it as SR. I will call it as SR m-1. Okay, and it depends on how many, the degree of the coefficients of the divisor. So this is how it's being done. You give u of x over here, you apply u of x over here, and you will get q of x. Okay, first you will get q of x, which is unnecessary, which you don't need, you don't need to know. You don't need this. What you need is the remainder. Okay, so first you apply the input u of x, and first you will get q of x, and after, when every input is being transmitted, after when every u of x, values of u of x, after when first this value will be transmitted, then this value will be transmitted, then this value will be transmitted. So after when every value is being transmitted, then at the same output you will get your p of x, you will get your remainder. That is how the working of the circuit takes place, right? So the reason, so now you need to understand why this everything is being fed back. This feedback actually means that if you look at this switch actually represents gm minus 1. This represents the second last one, which is gm minus 2, and it goes on. This actually represents g1. This actually represents G0. So what this actually, each of the switch actually means is that if the coefficient is 1, if the coefficient is 1, then there will be a short connection, okay? And if the coefficient is 0, it will be an open connection, okay? And also let me remind you that if the coefficient is 0, it will be an open connection. So if it is an open connection, then you don't have to draw the XOR operation because there is nothing to add. So in that case, you don't even have to draw the XOR function for any coefficient in which the value is 0. Okay, so this G0, G1, G2 actually represents the coefficients. So here if you see here, the value of G0 is 1, the value of G1 is 1, the value of G2 is 0, and the value of G3 is 1. And also we already know that you have already learned in the previous class that if you take the generated polynomial, the coefficient of the first term and the coefficient of the last term is always 1, which means this value over here is always a short circuit, and this value over here, this connection over here is always a short circuit. The remaining can either be open or short. That depends on the value of the in-between coefficients. Okay, so that's how we draw it. So this is like nothing, this is like just like how you draw the multiplication circuit. In the multiplication circuit, you are actually drawing a circuit in which you are using the multiplier as your and you are inbuilting the multiplier into your circuit. Same case over here also. Here we are drawing this division circuit based on the values of your divisor or based on the values of your g of x. There also in multiplication circuit also you are actually implementing the circuit based on the value of g of x. Here also same thing. You are going to draw the circuit, you are going to implement the circuit based on the value of g of x. Okay, so which means here the division circuit for this, the division circuit is, that is, I'm going to draw x cube u of x by g of x. Okay, I'm going to draw x cube u of x by g of x. So how the circuit looks like is, I will draw the XOR over here. Let me draw the XOR over here. Then I will draw the SR1. Then after that, I will draw another XOR operation over here. Okay. I'm not going to draw any XOR operation over here because there is no x square over here. That is why I'm not going to draw an XOR operation, which means the connection is open. So if the connection is open, over here and all, there is connection. Okay, over here there is a connection. Here also there is connection, but here there is no connection because there is no connection because x square is not there. So if there is no connection, then there is no need to draw an XOR for this. So you don't have to draw the XOR at every input of the shift register. Only where there is a connection, only you need to draw the XOR operation. So this is the circuit. That's it. This is the circuit. Very easy. This is how we draw the circuit. This is SR1. This is SR2. And this is SR3. Okay, and here you will transmit your u of x, and here you will send these values over here. All these values you will send it into the shift register. After every XOR operation, it will be shifted and then it will be fed back to the input, and then the value that you get, that is the value that you get, the quotient that you get, will be multiplied with your divisor, or this quotient will be added, will be XOR with this operation over here. This XOR operation is what is represented by this feedback operation. So you will get This is the circuit. This is the division circuit. This circuit is the representation of this. Okay, x cube into u of x means you need to have 3 shift registers. Okay, and wherever the value of g of x is there, wherever there is a coefficient, for there only you need to draw its corresponding XOR function. This is the working. So here, if you look over here, this is, we know that g of x is equal to 1 plus x cube, right? That is your example. 1 plus x cube. That is what I have written over here. That is, this connection over here represents 1. This connection over here represents x, and there is no x square. That is why this is an open connection, and that is why there is no XOR function, and this connection represents x cube. So that is how you need to draw your division circuit. That is based on the presence of the coefficients in the polynomial. Okay, for every degree. So here there is 1, here there is x raised to 0, here there is x raised to 1 and x raised to 3, and x raised to 2 is missing. So that is why x raised to 2 you haven't drawn any connection. This is how you represent the coefficient. So at the coefficient, what happens is that this is u of x, right? What is the u value of u of x? This is your u of x, right? 1 plus x square plus x cube. So first what happens is that first the coefficient of x cube will be transmitted, then the coefficient of x square will be transmitted, then the coefficient of x raised to 0 will be transmitted into the circuit. And while these 3 values are being transmitted, the output over here, right, you will get the value of q of x first. First you will get q of x, and the first q of x you will get is x cube. First you will get the coefficient x cube, then you will get the coefficient, then you will get the coefficient of x square, then you will get the coefficient of x, then you will get the coefficient of 1. Okay, but before that, when you're going to shift, right, immediately this when you're going to shift the value, right, this value, it takes time for those values to reach over here, right? So during all those time, the value of qx will be 0. Okay, during all those time, the value of the q of x will be 0, and after when it becomes 0, the next value will be x. You will get the coefficient of x cube, then you will get the coefficient of x square, then you will get the coefficient of x, then you will get the coefficient of x raised to 0. This is how you will get q of x. And after when u of x is being transmitted, so now u of x is transmitted, okay, u of x is completely transmitted. Now after when u of x is transmitted, you will be transmitting a bunch of zeros. And if you ask me how many zeros you're going to transmit, since there are 3 shift registers, you need to flush out the remaining values. So you're going to apply that many zeros in order to flush out the remaining values, because that remaining values is actually your remainder. So from here, at this point, once when you finished getting all the values of the coefficient, then you will start getting the value of your remainder. And here the remainder is nothing but 1, which means first you will get 0, then you will get 0, and then you will get again, you will get 1, because here the value p of x, right, p of x is actually will have 3 terms, because p of x is actually a degree of n minus k, it's a degree of n minus k minus 1, or it's 3 bits. So 3 bits means the value you will get only 1, so it will become 0 0 1. This is the value you are supposed to get, 0 0 1. So first you will get 0, then you will get 0, then you will get 1. This is how the working of the circuit is. Okay, so this working can be better explained if I'm going to actually draw it in your actual encoder itself. Okay, so here I'm not going to explain the working of the division circuit, because there is no need for you to understand why q of x is used. See, you don't need to see the creation of u of x. That's not important to you. What you need is the remainder, because the remainder is where you get p of x. And once if you get p of x, you have found already u of x is available to you. So once if you get p of x along with that, then you got your systematic cyclic code word. Okay, so this is what you need to focus. So what I'm going to do is that I'm going to draw your actual encoder. Okay, I'm going to draw the actual encoder, and in that actual encoder, a part of that circuit will be your division circuit. That's it. That's what you need to understand. The part of it will be your division circuit. So that is what I'm going to draw here. Okay, so how the circuit will looks like is, let me draw that first. So first you have a shift register. Okay, remember, just notice that I have not drawn the XOR function. I will tell you the reason why I have not drawn the XOR function later. Okay, so I will draw the SR1 first, and then I will draw the remaining will be the same. I will draw this XOR function over here. Okay. So I will just draw this. Okay. Then I will draw the next shift register, that is SR2. Then I will draw SR3. Okay. And then what I'm going to do is that after this XOR function that I didn't draw, right, I'm going to draw that over here. Okay. I'm going to draw that over here, and this is how my circuit will look like. Okay. And then what I'm going to do is that I am going to draw another circuit down here. I will draw this. So this is where I will get my output. Alright, and I'm going to draw a switch over here, and I'm going to draw another switch position over here, and this is the actual circuit of your encoder. Okay. This is your output. This is your output, and it's called as V of X. And here this value will be given to a gate, G-A-T-E, a gate. Okay, a gate that is used to block your signal. Why you're blocking is because, like I said, you don't need the quotient. Quotient is not relevant over here, right? And you'll get this is your circuit. This is the circuit over here. Okay, if you look at this circuit over here is the same part over here. Both the circuit are actually same. Okay, the only thing is that I'm controlling the operation of the circuit using this gate and this switch. Okay, the exact circuit is over here. Only thing is that I shifted my XOR operation, this XOR operation over here, because the thing is, like I said, I don't need to know what's my coefficient is. Okay, so I don't need to know my quotient is, my quotient polynomial. I don't need to know what is that. I only need to know the remainder. So to do that, what I will do is, how this is going to be done. Okay. So first, let me say, let this be the switch position 1. Okay, or okay, I'll give this is switch position 2, and let this be switch position 1. Okay. So like I said, V of X will contain both P of X and U of X, right? We know that. So first thing what it is going to do is, V of X is going to receive U of X. That is the first thing it will do. It will receive U of X. So at the start of this procedure, the switch is at position 1. Okay, the switch will be at position 1. So when the switch is at position 1, the gate is turned on. The gate is in on position and the switch is in position 1. So at that time, what I'm going to do is I will transmit my U of X. So what is going to happen during that time? When U of X is being transmitted, that U of X will go right at the output, right? It will go right at the output. So therefore, you will get the same value of your U of X. That is, you will get the same value over here. The same value. First, this one will be transmitted, then this one will be transmitted, then this 0 will be transmitted, then this one will be transmitted. That is what is going to happen. First, I will transmit 1, then I will transmit 1, then I will transmit 0, and then I will transmit 1. That is how I am transmitting 1 0 1 1 into V of X. Okay, that is what we need right now, right? If you look in the previous case, that is what we actually need right now over here. Right, that is what we need right now. That is, here you need both U of X and P of X, or if you look over here, you need to first, you will get these values. That is, you will get first these values, this value, this value, this value, this value, up to here. you'll get all these values first, starting from the highest order. You'll get the highest order, then you'll get the second last highest order, then you'll get the third last, and goes on, and you'll get up to here. So from UK minus 1, UK minus 2 up to U0. This is how you'll get your output over here. So first you'll get this one, then you'll get this one, then you'll get 0, then you'll get this one. Okay, and during that time the switch is at position 1, so it will get u of x, and this gate is turned on. So what is going to happen is, while you are receiving the value of u of x, while you are receiving this input sequence, at the same time the division process is going on inside it. The division process is going on inside it, and the quotient is actually being generated. But since the switch is in position 1, those quotient values will be discarded. Okay, the quotient will actually be generated over here, but it will be discarded because the switch is in position 1. Okay, so you don't need to know the coefficient, the quotient polynomial. What you need is only the remainder. So that is why when the switch is in position 1, the v of x, the output will receive the input sequence as it is. It will receive the input sequence, and then after receiving all the input sequence, or in other words, after when all the input sequences have entered into the division circuit, the calculation of the quotient will be over. Then what remains inside will be the remainder. Then what happens is that the switch from position 1 will go to position 2. So when it goes to position 2, what happens is that the remaining values of the remainder will then go into the position 2. Or the remainder values will be sent to v of x, that is your p of x values. So therefore, after this, when the switch is in position 2, first it will receive this value, then it will receive this value, this value, this value, then it will receive p2, then p1, and last it will receive p0. This is how the working of the circuit is done. This is how the circuit is being worked out. So to explain this, what I'm going to do right now is I am going to explain the circuit again using the table. Okay, so to explain using a table is actually more fun, so you can understand how this working is. So for that, what I'm going to do is I'm going to use the first table will be your shift cycle. Okay, cycle number, shift cycle, or okay, and then the next is that the input bit, which input bit is I'm going to enter into the circuit. Okay, input bit, and then I need another column to represent the contents of my shift register. Okay, that is SR1. This represents SR1, SR2, and SR3. Okay, and this is my output. This output means this output over here. What I meant output is v of x. V of x. Okay, this is u of x. Okay, this actually represents u of x, and this actually represents my v of x. That's it. This is the only thing you need to explain how the operation is being done. So what is going to happen is, let me tell you now itself. Oh yes, I will give you one more. So let me give you another column also to explain this circuit. I will use another called a switch position. Okay, whether it is in position 1 or position 2. So switch position. Let this be another column. Okay, so you will understand in which position the circuit works in. So in that case, okay, first what happens is at the input. Let me talk about the input. So input is, what is the value of input? U is equal to 1 0 1 1. Okay, so first I will transmit this 1, this 1, this 0, and this 1. That is, first I will transmit this 1, this 0, this 1 0 1 1 1 0 1. Okay, that is the last bit is what you're going to transmit first. So 1 1 0 1, and then what you're going to do is you're going to clear out the remaining shift register, so you'll get 0 0 0. So you need to understand that during the transmission of this bits, your output will be the output of the division circuit will be the quotient. Okay, and during this time you will get the remainder. And also you need to know, so here if you look over here, during the transmission of your input bits, the switch will always be in position 1. And from here onwards, the switch will be in position 2. Okay, that is also you need to understand. So what you need to know is the value of your shift registers. Okay, so V of X is your output. Let me show you the output. This is the output. Okay, and the switch is in position 1. So let's start now let's start explaining the circuit. So this is the first shift cycle, second shift cycle, you'll send this, third shift cycle, fourth, fifth, sixth, seventh, and it goes on. Okay, this is the last one. So let's see how this is being done. Okay, so first what is going to happen is, let me say the switch is in position 1. Okay, the switch is in position 1 and your first input bit is 1. So which means 1 is being transmitted. So if 1 is being transmitted, your output will also be 1. So if 1 is being transmitted, the output will be 1 itself. Okay, the output will be 1 itself. Now let me write the output first. Okay, first I'll explain to you using the output. So if the switch is in position 1, the output will be your input bit itself, because the same value will be transmitted at the output. Okay, so you will get 1 1 0 1 itself. You will get 1 1 0 1 itself. Okay, now let's talk about the shift registers. What will be the value of the shift registers? So how to explain to you the shift register is, first you need to look at the every value of the shift register. What is the value of SR3? How do you write the input of SR3? The input of SR3 is SR2 itself. Okay, that is, the input of SR3 is nothing but the SR2 itself. So that is one thing you understand. So this, let me just write that so that I will remember for my own calculation. So this is, SR3 is nothing but the input, the output of SR2. Okay, the input of SR3 is the output of SR2. What about the input of SR2? If you look over here, the input of SR2 is actually this arrow mark and this arrow mark. Okay, and what is this arrow mark? This is SR1. So SR1 plus this arrow mark. And what is this arrow mark? This arrow mark is from here. It's coming from here, which is SR3 plus U of X. So this SR2 is equal to SR1 plus SR3 plus U of X. Let me write that over here. So SR2 is equal to SR1 plus SR3 plus U of X. That is your input. That's your input. Okay, that's what it means. Input is U of X. That's what I meant. SR3 is this value, SR1 is this value. That's how you write the input of SR2. Now, how will I write the input of SR1? What is SR1? If you look over here, this is SR1. SR1 is this arrow mark. This arrow mark represents nothing but you will be sending a bunch of zeros. That's all, nothing else. Okay, and you don't need, actually the what this means is that at a time only one of these two will work. Okay, either this arrow mark, first this arrow mark will be the one that will be transmitting the message, and after, when this switch is in position 2, then the zeros will be sent. Okay, so for now you can ignore this. Okay, you can ignore this, or you can just say it's sending a bunch of zeros over here. That's all. Okay, so this arrow mark over here represents the operation. So this arrow mark is nothing but, let me see, it is coming from here, which is SR3 plus U of X. So this is SR3 plus U of X. So how to write SR3? Simply copy it from SR2. How to write SR2? Is nothing but SR1 plus SR3 plus input. And what is the shift register 1? It is shift register 3 plus U of X. So let's start calculating right now. So now here, initially we know in the first, before transmitting of the first shift cycle, the output will always be zeros, right? The shift register will always be zeros because no value has entered. Okay, so now when you're at the first shift cycle, what's going to happen is that, like I said, SR3 is equal to SR2, which means this 0 will be transmitted over here. Okay, this 0 will be transmitted over here. And what about the value of this SR2? It is nothing but SR1 plus SR3 plus input bit, that is 0 plus 0 plus 1, which is 1. And what about SR1? It is SR3 plus U of X, that is 0 plus 1, which is 1. Okay, this is the contents of the shift register after the first cycle. Now what happens after the second cycle? And the second cycle, this 1 will be transmitted to SR3 because SR2 is equal to SR3. So this 1 will be transmitted to SR3. And what about SR2? It is SR1 plus SR3 plus 1 or plus input bit. So that means 1 plus 0 plus 1. 1 plus 0 plus 1 is 0. Okay. 1 plus 0 plus 1 is 1 plus 1. 1 plus 1 is 0. And the SR1 is 1 plus 1. Sorry. 0 plus 1. 0 plus 1 is 1. Okay, so this is the value. Next is you got to write the value of SR2. Also next after the second shift cycle, at the end of the third shift cycle, what's going to happen is that this 0 will be transmitted over here. The value of SR2 will become 1 plus 1 plus 0. 1 plus 1 plus 0 is 0, and over here you will get let me see, you will get 1 plus 0, which is 1. Okay, now next what will happen so here up to this point that you're seeing here, up to this point that you're seeing here, the switch is in position 1. Okay, and you will get this output. All right, so now what is going to happen is that the switch over here at the end of the third shift cycle, so at the end of the first shift cycle you will get this, at the end of the third shift cycle you will get this, at the end of the second shift cycle you will get this, at the end of the third shift cycle you will get this. Now at the end of the fourth shift cycle, this 0 will be transmitted over here. Okay, and this will become 0 plus 1 plus 1. 0 plus 1 plus 1 is 0. Okay, and then what happens over here, it becomes 0 plus 1, which is 1. So at the end of the fourth shift cycle, right, at the end of the fourth shift cycle, this is a 7/4 cyclic code. So at the end of the fourth shift cycle you will get 1 0 0. Okay, and then the switch, then this what happens, the switch will go to position 2. Okay, so to go to position 2, the position 2 is actually nothing but, if you look over here, when the switch is in position 2 is actually nothing but the value of SR3 itself, the same value of SR3. So when the switch is in position 2, the value of SR3 will be transmitted to the output. So when the switch is in position 1, the value of the input will be transmitted at the output. When the switch is in position 2, the value of SR3 will be transmitted to the output. So all I need to do is simply copy the value of SR3. So what is the value of SR3? If you look over here, since the switch is in position 2 and also the gate is turned off, which gate is turned off means then all the values that you see here will become 0, because no value is being permitted now. So since this gate is turned off means this connection will become open. So all these values will become 0, which means this is nothing but a pure shifting operation takes place, nothing else. That is why you are giving the input as 0 over here. That is what this actually means. That's what it actually means when I written over here. So from here onwards, pure zeros will be entering into the circuit, and all the values of the content of the shift register will be shifted out. So that means first you will get, so first the value at the switch position, first this 0 will be shifted. Then what happens is that this 0 will be shifted over here, this 1 will be shifted over here, and this 0 will be shifted over here, and you will get, again you will get 0. Then what happens is that this 1 will be shifted over here, this 0 will be shifted over here, and this 0 will be shifted over here, and therefore the output will become 1. So this is your remainder. This is your U of x, and this is your P of x. See, you got the remainder, you got the input message, that is same message that you sent over here, the same message you got over here, and this is your P of x, which means your V of x, is actually will be looking like this. That is, if you want me to write, I will say like that is, first I'll write this, then I'll understand. This is 1 0 0 1 0 0 1 0 1 1 1 0 0 1 0 1 1. This is the output that you will get. First you will get this, then you will get this, then you will get this, then you will get this, after that you will get this, this, and finally you will get this. This is how it did. Okay, this is how it will be done. This is how the output will look like. Or in other words, your v of x. Now I can say what is v of x, right? V of x is 1 plus this is x square, this is x cube, plus this is x raised to 4, this is x raised to 5, plus x raised to 6. This is your v of x that you'll get. This is how the working of the systematic encoding of systematic cyclic code is done. Okay, this is how we explain the operation. So now I will just show you the general block diagram of a systematic cyclic code operation. Okay, the general block diagram. This is the encoder of an NK systematic cyclic code. This is the actual block diagram. Okay, so here, like I said, this is actually a generalized version, which means here you will have n the output, the contents of the output polynomial will be, the contents of the output bits will be n, and the number of input bits will be k, and hence you will get a generated polynomial, and this is represents g0, g1, g2, g3, gn minus k minus 1, and finally gn minus k. And we already know that for the generated polynomial of a cyclic code, the coefficient of the first term and the last term will always be 1. That is why this arrow mark, and this arrow mark will always be there. The rest of them depends on the value of the in between coefficients. Okay, so which means that if g1 is equal to 0, then this arrow mark will be absent, and also this XOR function will also be absent. Okay, so we don't need to draw the XOR function of that. So here the working of the circuit is exactly how I explained before. First is that the switch is in the position 1. Okay, at the beginning the switch will be in position 1, and during that time, to allow the transmission of the message bits directly to the output during the first k shift, where k represents the number of input bits. So u of x has k bits, right? So the first k bits will be transmitted into the output. That is the first step. At the same time, okay, that is when when the input bit is transmitted to the output, the gate is turned on. The gate is on. This gate over here is turned on. So therefore, this u of x will also be transmitted into the division circuit. So at the same time, the gate is on to allow the transmission of the message bits into the n minus k stage division shift register circuit. That is this division circuit. Okay, so therefore u of x, so during at position 1, u of x will go to the output, and u of x will go into the division circuit. Okay, and the division circuit will start calculating the quotients, which you don't need to know. That's what. Now, at the transmission of the kth message bit, the gate is turned off. The gate is turned off, which means now all the quotient values have already been finished calculating. Now the remaining values will be the remainder. Those are the remainder values. That is P0, P1, P2 up to Pn minus k minus 1. These are the remainder values. So the transmission of the kth message bit, the gate is turned off, and the switch is moved to position 2. The switch is moved to position 2. Okay, so n minus k zeros are introduced into the shift register. Zeros will be introduced into the shift register to move the parity bits, that is these remainder values, to move the parity bits remainder to the output. So when the switch is in position 2, this will become a symbol shifting operation, and all the values of the parity will be shifted. First, p of n minus k minus 1 will be shifted over here. Next, the value before that will be shifted over here. Then the value that comes after that, and after that goes on. Then p2 will be shifted. Then after p1 will be shifted to the output. Then finally p0 will be shifted to the output. Okay, so that's what it means. N minus k zeros are introduced to the shift register to move the parity bits remainder to the output. Hence, that's it. That's the only working. Hence, the total number of shift is equal to n, and the contents of the output is the code word polynomial. That is this polynomial that you have written here. As v of x is equal to p of x plus x raised to n minus k u of x. That is this polynomial right here. Okay, this polynomial you will get. The encoder, after when all the zeros have been transmitted, so now every shift register values have been cleared, all the values have now become 0. Hence the encoder is now ready to take up the encoding of the next message input. So this is the working of the encoder of a systematic NK cyclic code.